Hello everyone, and hello from Princeton University, where I'm still at the workshop. So I'm going to record another video to walk you through some of the material that instead of the class on Friday. Let's get going. So I'm going to continue with the motivation, and this is following lecture 1.1 slides that I have uploaded to Canvas and sent along a couple of days ago. So let's get to the... Alright. So I'm just gonna walk essentially over the videos that you were supposed to watch already that I posted in an announcement. And a lot of those videos are talking about the history of computing. So let's place computing in the general scientific quest. So when we actually look at the science versus engineering in the quest for knowledge, let's remind ourselves that scientists typically seek to understand nature at its core, and they isolate a single element of nature in order to understand it, and basically they try to find the fundamental laws of nature and how that affects whatever it is that they're studying. Engineers, on the other hand, they design and build things that work with those fundamental laws, so they depend on science to find them out, but they're kind of trying to figure out, okay, which laws are the most important ones, because they're trying to predict much more complex systems, and they can't necessarily always isolate things. So in that sense, they have to figure out what is the most important thing so they can predict the behavior correctly. So they kind of integrate things much more than they isolate them. They isolate things, I guess, only when they're trying to fix them. So in that sense, petroleum engineers deal with some of the most complicated situations that happen in subsurface, and most of the time you cannot see what is going on. Now, what are the tools, whether you're doing science or engineering, what are the tools that you can have to build the knowledge? And the pictures here that I have actually hint at those. So Einstein is famous for his theory, so one of them is theory. The second one is experimentation. So you build a system that you can literally play with in the lab and figure out what is going on. But when you go in there, you kind of build on the knowledge that came before you, so you already have some idea of what it is that you want to study and how it is that you want to design it. And then we also, as of recently, and computers allowed that, we have computation as well. It's sort of a lab on its own, it's just virtual. Apologies. So in that sense, computation is the most recent tool, but it's becoming a very powerful one. Now, I'm not going to play another video. I've been posting a lot of videos. You can follow the link to see Dr. Oden from University of Texas. He's from one of the institutes here, Institute for Computational Engineering and Sciences, to explain the computation and how powerful it became. It's really a very short video, and it's also what motivated him to become a computational engineer. So to place the rest of the history, so I hope you watched the videos. If not, this is to motivate you to watch them. We today wear powerful computers. Everybody has a phone. That is a very powerful computer, much more powerful than the computers that NASA had in 1960s and 70s when it was sending people to the moon. So in that sense, we have to actually really understand that this thing that we use to like pictures of cats on Facebook is actually a really powerful computational tool, and it can do a lot. Now, the computers started in 1830s. At that point, they were conceptualized as mechanical devices. So whatever storage of numbers you had in that computer, you had to have literally metal wheels with digits in order to actually store those numbers. So that was, of course, pretty cumbersome and built. And the TED Talk that describes this first mechanical machine it has been sent to you already, and it's also linked in this presentation. There's also more detailed, but still very brief, of history of computing that kind of walks you through the stages of technological advances that were huge jumps in the ability to compute, and that actually brought us today to these variable computers, and some of you have much smaller, like watches and Fitbits, that exist in almost nearly every device. These days, if you want to, there is a small computer on your any kind of cooking device at home, like a slow cooker, and you can start it from your phone, because as long as you're on a wireless network, they can communicate. So these things are pretty powerful. Now, if you wanted to look at the early gallery of computers, one of them is shown here, ENIAC computer from 1946. There's a link for you to follow. So it's, again, a little bit of history. And those are the times when computers filled in entire rooms. Also, at the same time, they kind of needed like a mechanical crew to always constantly change the parts that were burning out daily. So they also required much more maintenance than the computers require today. And basically, there's one of the first computers showed in NASA Space Center in 1961. In 1963, there were only 15 total computers in the entire state of California. And in 1973, as Dr. Bomer shows in his video on punch cards, there was one computer on the entire UT Austin campus, and everybody wanted to use that one computer. And I highly suggest, there's a number of movies that actually go just simply the time period that they were set in, that review that history, and Hidden Figures is one of those movies. It's a complicated movie, actually. It highlights how important computing was in the space race in 1960s, and at that time, human computer was a job. So mathematicians were actually performing calculations that modelers, engineers, physicists were coming up with, in this case, spatial motion of both the rockets and orbits and so forth. And those calculations were computed by human computers. I still kind of chuckle at the notion of a human computer, especially since I myself have a math background. So some number of years ago, I would have been a human computer. So, and I don't think of myself as a human computer today. So in the course of the movie, those happen to also be in the movie black female mathematicians that were these human computers, and the movie follows them. So it also shows this huge technological changes that were in the progress, and installation of the first computer that actually threatened these jobs. So there is also like this entire dynamic of what do you do in the eyes of changing technology. So it shows how and they had to overcome a lot of adversities, and they had to persevere and do a lot of hard work and show vision of where they're going as the technology is changing. This is something that is timeless. We all face technological changes in petroleum engineering specifically. So it's kind of a very good movie to watch in that sense. It kind of shows also what it means to be inventor and engineer and have a vision and move forward. So in that sense, I recommend it as something that puts the history of computing in the context of all of the other societal changes. So computational engineer to date is a powerful career path, and this course is supposed to open you up to that path. Whether you take it or not, that is solely up to you, but it is a powerful tool that every engineer should know. So as the course progresses, some of you will face programming for the first time. And programming in itself, it takes patience to learn. Oh, just like any skill, really. And there will be a lot of, maybe you will be mad at this course a little bit. Okay? Now, and sometimes you will be mad at the software that you're using. Now, in that sense, I think this video interview on punch cards is very illuminating, because if you think that computing or programming is painful now, then I don't know what it was in the 1970s. So technology was very different. So it was actually really painful to program. You had to typeset your programs, then take them to the central computer. Then there you will find out, oh, there's a bug in the program. And then you have to do this walk all over again, not to mention what happened if you lost your punch cards or spilled them on the street and so forth. So in that sense, we can actually use these things to do our homework in PGE310 these days, and that's pretty powerful. So I encourage you to watch the video. I will now walk over a few numerical methods examples, just to give you a taste of what the numerical method is, what it actually strives to solve, and a little bit of intuition of how is it done. And then we will actually, over the course, go into more details. So many mathematical problems, let's say that you're solving a quadratic equation. That quadratic equation has solutions. You have a formula for x1 and x2 that solve a quadratic equation. So in that case, we say that you have an analytical solution. You have a formula for it. So there's a math solution to it, pure math. Now, numerical methods are typically designed for problems that don't have a formula. They are posed in terms of equations, but those equations are not necessarily easy to solve. So in that case, we typically design numerical methods that look for approximate solution. So that solution is not supposed to be the solution, but it's getting close to the solution, and that close enough is enough for us to work with. Okay? So the process of applying this numerical method is typically called computation. Programming is what I need to do to write instructions to the computer to perform this numerical method is essentially what's called programming. Now, most of the problems, real-life problems, actually require numerical techniques. A very small fraction of problems have a closed formula solution of the type that you're looking for in your calculus classes, for instance. And that process can take quite a bit. So we will typically work on smaller problems that take not even a minute to solve. We will push that boundary once just so that you get a feel for it. But it is actually quite common for some problems that are on the edge of what science can do, that you will have 50,000 powerful computers work for 3 months to actually compute. Now, here's the first example. So I have mentioned quadratic equation, and we can imagine this equation that we are actually solving. We are looking for roots of it. So we're finding x's such as this expression, this function of x is equal to 0. So if we formalize it like that, we're looking for root x of a function f such that f of x is equal to 0. Then we're actually framing it in some general way so we can form a whole lot of problems that are not necessarily quadratic equation in that way. So this has an exact method, and we actually have a formula. So we're not necessarily interested in a numerical method. However, here's another example, ideal gas, that is very close to what engineers have to compute. So in that case, the pressure, the volume, normalized volume, and temperature are related in this simple ideal gas law. So PV is equal to a constant RT. Now, this is ideal gas law. Most of the gases are not ideal. They don't behave in a simple way. So we have actually much more complex relationship. So in this relationship, if you give me volume and temperature, I'll give you pressure. If you give me any two of them, I'll give you the third one among these thermodynamic variables. Now, in that sense, if you have something more complicated, such as Peng-Robinson equation, which relates pressure, temperature, and volume in this relationship, and there is R is a constant here, A and B are two constants that depend on gas itself. R is universal constant. Then this equation is not easy to solve. You can't simply give me pressure and temperature and I'll give you volume back. Okay? Not easily for sure. This is not easy to solve. So in that case, we don't have a formula. So question is, how do we approach a problem? So here's one way. One way would be to simply, well, plot it and kind of see, for given pressure and temperature, plot possible V's and see what happens. And something that actually this formalization in terms of expressing this is function of volume, such that for given pressure and temperature, let's say that it's 50 bars in temperature of 473 K. So if I put that in, I will put everything on one side, so I'll have pressure minus all of these terms. So pressure minus this term plus this term is equal to 0. So I have formalized that in this expression, f of something, in this case v, is equal to 0. Now what? We could just try to plot this and see where does this function intersect 0. That's one way. If we don't have a plotting calculator, then maybe we can just try a couple of values. So one good ballpark figure would maybe be this volume that ideal gas gives me. If I have to guess, I may as well guess something that I can compute, and maybe it's not that far off. So here's one of those volumes. Okay, so let's actually see around these values. Let's compute a bunch of values around this one. So if I actually compute f of 786, I'm going to get something close to 2. Then if I go a little less up, I will get a negative value. I have a positive value and a negative value. In between somewhere, maybe I hit 0 if this function is continuous in between. Cool. So I will let me try a function right in the middle here. A value of v right in the middle here, 768. If I do, I'm still positive, but I'm closer to 0. Let's now try in between these two values, or rather in between these two v's, 759. I'm getting closer to 0. Now I'm going to keep this one and this one, and I will try in between those. This is actually a numerical method. It's an algorithm. It's a set of rules that tells me, okay, find two values that are surrounding 0, and then evaluate the function at the midpoint. See that you have a positive and a negative value, and switch to the smaller subinterval that you still have positive and negative value, and then look at the midpoint of it and keep going. That is one way. So actually this will be a method that we're going to program, and it's called bisection method. If I actually plotted, I would see that the root is actually indeed, when I zoom in, close to 755. Cool. So that was one example, and those will be root finding methods. Second problem I can have is differentiation. So I know how to differentiate formulas, and those formulas, so let's say that I work with this function, y is equal to x squared minus 4x plus 3. If I wanted to evaluate the derivative, dy dx, I know how to do that. If you want to take a moment and sketch this quickly on a paper and compute, please do. You can maybe pause the video if you need more time, but I will continue. So basically, okay, if I wanted to do that, just like as a derivative to compute, dy dx is 2x minus 4. So when I evaluate that at 1, that is equal to minus 2. But what if I had something rather complicated, or maybe data, not necessarily a function? How do I find the derivative? Well, it is a slope of the line tangent to the curve. Okay, so in that case, here's my curve, and I could try to find this slope. Okay, so that is one way to actually, now this slope I can also approach. So if I don't have a way to just draw it and find this rise and run, I could also simply take 2 points around it and simply draw a line that approximates, and I will always find the slope, and then I can get those points closer and closer and closer and closer, and I will zero in on derivative. Okay, cool. Now let's look at the third example, and that's going to be our last example. Let's look at the area under the curve. So if I had to integrate, which gives me the area under the curve between 0 and 1, I would know actually how to compute this integral. So if you want to pause the video for a moment and calculate it, please do. And if not, I'm just gonna continue. So basically, we know how to integrate. We have the rules. This is 1/3 x to the 3 minus 2x squared plus 3x. And I evaluate that between 0 and 1, and I would get 1/3 minus 2 plus 3 minus zeros. So that gives me 4/3. So this is again analytical solution. However, sometimes I don't have a formula available, or this could be rather complicated function, and I need approximate methods. In this case, for integration, what we do is we again imagine plotting a curve, and I will divide this interval between 0 and 1 into a number of subintervals. On each interval, I'm going to draw a little box. This is the value of this function at this point. And I'm just going to continue or approximate this function on this entire interval with this value. This gives me a very simple area. It's this height times this width. And I can sum up all of these areas. Obviously, I'm making a mistake. And this is sort of the size of the mistake. This plus this triangle plus this triangle plus this triangle. Okay? However, as these intervals get smaller and smaller, I will actually, as I get the smaller intervals, my error will get smaller too. And that's also a numerical method, and we will actually get close, or as close as we want to the result. So if you actually compare the answers for 4 rectangles, this area is 1.72, let's say. For 10, it's this number. For 100, it's this number. For million, which computers easily go and compute, is 1.33333. And actual value is 4/3, which is 1.33333. So I converge to a result. So that is another example of a numerical method. So in this process, especially when we have rules or algorithms that we can follow in a ordered fashion, computers are gold. They can repeat and do calculations with much more precision than people do. So it will take a number of iterations, but you cannot just let the computer do it. So you might need to repeat something a million times. For a computer, that's not a problem. So computers solve things faster. They have some error, but they make error rather consistently. So we can actually kind of have some idea of what the size of the error is. With humans, that's not necessarily so. So there are some more human errors that appear than when they compute. So programming is actually writing a set of rules in a way that computer understands how to perform. It does take some practice, so you have to be very ordered, and you cannot make small mistakes. You cannot have a typo, because computer will not understand the text with a typo, which a human will. So in that sense, the computers are not they're very prone to make large errors when you make a rather small one, and they will not understand what you meant. You have to be very precise. That's what kind of makes programming sometimes hard, because it takes a lot of patience to read those errors out. So please don't get intimidated. It simply takes practice. Now how do we actually tell computer what to do? What are the set of rules, and they're actually called languages. So they're programming languages and environments. And some common ones that you learn programming in are MATLAB and Octave, Python, also Java, C and C++, Fortran, Visual Basic, and so forth. There's a number of them. There's generations, and they do change over time. So we will actually pick one of them that is actually getting very popular language. It's Python. You might have actually worked in Microsoft Excel that has scripting available through Visual Basic. So it's sort of like a macro attachment to the Excel worksheet. So that's a programming language as well, though Microsoft Excel in itself is a software package, and it's much more than just a programming language. All of the languages have certain structures that resemble each other. In that sense, if you learn one, it's going to be rather easy to learn others. And Python that we will use in that group, in the sense that its syntax is very commonly found in C, C++, Fortran, some as well. So they tend to differ in some sort of minor details rather than major things. And programming languages will change. You will learn one 20 years from now. There will be another that is much more popular, because languages, just like hardware, languages which are sort of underlying software, have to change and adapt as well. So it's a changing landscape. Just expect change. That said, there's certain logical structure to programming that is common, and what you gain in this class is a good foundation for the future. Okay? Without further ado, I'm just going to list here course topics. So we're going to start just with the introduction of linear algebra, because it's at the heart of a lot of computation. So, and specifically storing data and storing arrays. And then we will move on to Python fundamentals. We will not assume any prior knowledge. We will start from scratch and do some programming structures, look into some errors in debugging, and this is all preparation. Once we have our fundamentals and our tools built, then we will start numerical methods for root finding, numerical methods for systems of linear equations, numerical methods for curve fitting, ordinary differential equations, and hopefully, if time permits, we're going to introduce some on numerical integration. So this completes our introductory lecture, and I see you in class on